Welcome to Analog Microelectronic Circuits lecture. This is lecture 9, Unit 2, and we started a bipolar junction transistor in this unit, and we covered the structure, the structure, operation, the various configurations, and a small signal model. And in last class, we started about common emitter amplifier. So if you remember, we have yeah. First, we started with the finding the intrinsic gain of BJT, and we understood that the intrinsic gain is close to minus GMR naught, or if I write in terms of early voltage, it is VA by VT. We have done a comparison with MOSFET also there. Uh, After that, we looked at the common emitter amplifier. Right. Yeah. So common emitter amplifier. No, we arrived at the output impedance expression for a transistor when there is a resistance connected to the emitter, and the expression is almost same as MOSFET circuit. Then we started bipolar amplifiers, and there we have done common emitter amplifier. Gain, which is minus GMRC, including early effect, it is minus GM into RC parallel R naught. Then input impedance is R pi and output impedance is RC parallel R naught. So these things we have discussed. So now we'll see we look at a common collector amplifier. So common collector amplifier is otherwise called as can I know the name of common collector amplifier? Can I get a response in chat box? Common drain amplifier is otherwise called as source follower. In a similar way, what can we call? Yeah, it is a buffer. Emitter follower, yes. So common drain was known as source follower because it was following the source terminal. Uh, sorry, the source or the output was following input, and the output at source, whatever is given at input, source was following the input. In a similar way, here we call it as common collector, or we call this as emitter follower. Common collector or emitter follower. So since we have done the analysis for common emitter, I would request you guys to start with can you draw the circuit diagram of a common collector? So when I say common collector, collector should be common. Uh, Collector should be common in the sense that should be AC ground for the signals. Then we will have input to the base. This is BJT. Input should be given to base, which is Vin. Output will be taken from emitter through a resistance connected there. So output is the resistance is Re there, and this is output V out. Now collector terminal should be common, and we have to bias it properly, otherwise it will not work. So we will be providing collector voltage, we call it as VCC. But that will be this VCC will be AC ground, right? For AC signals or for small signals, this will be AC ground. So the collector terminal act as a common terminal, right? Now, okay, so we'll straightforward. We'll start with the small signal analysis itself. So can you draw the small signal model for the transistor, including this emitter resistance, and can you find the voltage gain of the circuit? Voltage gain. I'll give you 1 minute, 2 minutes time. You can try that and let me know. So you can draw the small signal model of the BJT, then modify that according to the given circuit diagram. That means you have to add a resistance Re, you have to connect, yeah, since your collector is connected to VDD, that has to be properly grounded. and you have to mark input and output, and then you should get the gain expression for the same. Madhusudan,
Yes, sir.
yeah, are you able to do that?
Sir, I'm trying, sir.
Okay, okay. Nishant, Nishant,
Yes, sir.
yeah, Nishant, you got the answer for this?
No, sir. Trying.
Okay. All right. So while you can try, I'll do that here. So first thing is we have to replace BJT using its equivalent. So the equivalent of BJT is this is GMV pi, this is R pi, and the voltage across this is B pi. This is the equivalent. So for the time being, I'll not consider R naught, or I'll not include the early effect component there. So this is the equivalent of transistor, this being collector, base, and emitter. Now I'll modify it according to the circuit. So at emitter, I need to connect resistance RE. This is RE. Collector should be grounded, and at the base I need to connect the input signal, which is equal to V in, right. Now this is the output point, V out. Now the objective is actually to find what is V out by V in, right. I can write one equation here. So if I apply a KCL at this node, let me mark this node. So there is one current from this branch, another current from this branch, and that will give you a current at the output terminal. So the current through the branch from the base, if I write it as V pi by R pi, because V pi is the voltage and R pi is the resistance. So I'll write this as V pi by R pi, that is a current from this side, plus the current from the collector side is GMV pi, that is equal to V out by RE. So our aim is to find V out by V in. That means I need to eliminate V pi, or I should get a substitution. I should be able to write V pi in terms of V out, right? So that is possible from this expression. So what I can do here is if I take this V pi common from here, it is 1 by R pi plus GM equal to V out by RE, or I can write V pi as V out by RE into uh, R pi by 1 plus GMR pi, right. So Pallavi, are you there? Pallavi.
Yes, sir.
So how can I substitute GMR pi? What is GMR pi?
Mm,
All right, Kiran Kumar.
Yes, sir.
Yeah, so how will I write GMR pi in terms of any other variable related to BJT?
Just a sec, sir. I'm like looking.
All right. So okay, anyone? Yes, yes, Mahesh. GMR pi is beta. All right, yes. So GMR pi is beta. So I can write here V pi as V out by RE into R pi by 1 plus beta, right? Uh, so this is V pi. Now what we can do is, so our aim to write V pi is, say why we try to get an expression for V pi is to substitute for V pi. Now if I write the relationship between input and output by looking at this branch, I can say that V in is equal to, V in is actually from this point to ground, that V in is equal to the voltage across R pi plus voltage across Re. Voltage across R pi is V pi and voltage across Re is V out. So I can write V in as V pi plus V out. V in is V pi plus V out. So by substituting V pi here and by rearranging, I can definitely write it as V in is equal to V out by Re uh, into R pi by 1 plus beta plus V out, or this will give V out by V in as V out by V in can be written as 1 by, will be 1 by, right, V out, yeah, so it is 1 by 1 plus R pi by beta plus 1 into 1 by Re. Yes, so it is 1 by 1 plus R pi by beta plus 1 into 1 by Re, right. Now how can I write R pi by beta plus 1? Any substitution can I do there, or any approximate value? Yes, it is Re, or it is 1 by Gm. Yes, very good. So it is 1 by 1 plus. So we know that R pi is Re into beta plus 1. So R pi by beta plus 1 is Re. So Re is actually, we will write Re as 1 by Gm. In fact, it is alpha by Gm, and alpha is a value which is very close to 1. So I can substitute this as 1 by uh, Gm into 1 by Re, right. Yeah, so or this can be further written as, this can be approximated as Re divided by Re plus 1 by Gm, or this can be written as Gm Re divided by 1 plus Gm Re, which is same as the MOSFET amplifier expression. There we wrote it as GMRS by 1 plus GMRS. I hope you remember that. All right. So yeah, if you have doubts, you can ask. Otherwise, we'll move. Now I'll request you to find the input impedance of the stage, common collector stage input impedance. So while evaluating input impedance, if you have doubts, you can check. So you can definitely make a comparison here. In case of common drain, it is GMRS by 1 plus GMRS. And one more thing, if you are including R naught, you can see that R naught will be an element between collector and emitter. So that will be, in effect, that will be in parallel to Re, right? So if you are adding an R naught here, R naught is actually coming in parallel to Re. So you can modify the final expression by substituting R naught in parallel to Re. So including early effect, I can write V out by V in as Gm into Re parallel R0 divided by 1 plus Gm into Re parallel R0. Right. All right. So since voltage gain is done, we can find what is the input impedance of the circuit. This can be written in terms of a small re as well. So okay, that also I'll write here. So Gm, if I take Gm common from here, I can write this as Re parallel to R0 divided by small Re plus Re parallel to R0, because small Re and Gm are inversely related, right? So this way also you can write. You will find that different ways of expressing by just changing the parameters. All right. So let me try with input impedance now. So this I want you guys to try, and I'll just ask one of you. You can tell me how you have done. Right. So input impedance is very simple. You can retain the same equivalent circuit. Input impedance. When you find input impedance, you have to connect a test voltage here. Call it as V test, and you should find what is V test by I test. Right. So let me place this equivalent circuit here. On that I'll work on. All right. Yeah, I think Karthi, you're trying to give the answer, right? So let me check with one of you. Um Ashwit Kumar. Ashwit Kumar. No problem. No problem, Karthi. Ashwit Kumar.
Yes, sir. Hello,
Yeah, Ashwit, you are attending the.
sir.
This is your initial. I haven't seen your name yet.
My full name is Penubadi Ashwit Kumar. It is.
Oh, okay. So from when you are attending classes? From the first, from
Yes,
September?
sir. Yes, sir. From the first time attending the class.
Oh, okay. Then I missed your name. All these days I haven't seen, and I'm calling you for the first time, right?
No, sir.
Oh, okay, okay. Because I am seeing your name as Penubadi Ashwit Kumar now. Okay, okay, Ashwit. Tell me, Ashwit, and how to get the input impedance, or did you get the input impedance expression?
No, sir. I'm still trying to.
What you are trying? Just let me know. I'll also help you. What we have to do first?
Uh, have to use the KVL for the
KVL for the
C at C.
Y at C.
Sorry, sir. At B. We have to find input. So at B.
Yeah. So first, what I should do to find input impedance? Any idea, Ashwit?
No, sir. I'm not getting it.
No, to find input impedance, what I should do first? What is the procedure to find input impedance? Are you able to recollect, Ashwit? All right,
No,
what you have to do is you have to connect a test voltage, right?
okay, sir.
This is V test and this current is I test, and then you have to perform the rest. All right, Ashit, I'll do watch and make sure that you understand this, right? Yeah. So you can unmute. You can mute Ashwit. Yeah. So V test can be written as V test is equal to uh, V pi, which is the voltage drop across R pi, plus the drop across RE. Now, when I write the drop across RE, I know that there are two currents coming. One is the current from here, and another is the current from this side, which is the GMV pi. So the total current or the current through RE is one is I test. I test is one current, and the current from other side is GMV pi this into RE. This is actually V test. Or this can be written as what is V pi? V pi is again I test into R pi. So V pi can be written as I test into R pi plus I test plus GM into I test into R pi into RE. Now you can see the entire expression is having only V test and I test as the voltage and current variables. So you can write what is V test by I test from this. That is equal to, first term it is R pi plus here it is 1 plus GM R pi into RE, or this can be written as R pi plus beta plus 1 into RE. R pi plus beta plus 1 into RE, and yeah, so this is the input impedance expression for common collector. So any doubts in this? I think some of you have responded here. RE into beta, yes, plus R pi, yeah, it is beta plus 1, okay.
Sir,
Yes, yes, Naman.
so, if I try to simplify this equation, can I also write it as GM R pi RE as a final equation, like we used to do it in MOSFET?
Yeah, so yeah, by looking at the okay, now the difference is what is R pi? R pi is beta plus 1 into RE, right?
Yes, sir.
Plus beta plus 1 into capital RE. So in fact, this is beta plus 1 into RE plus RE. Now you can say that if RE is small, you can write this as beta plus 1 into RE with that understanding.
Okay, sir.
All right, yeah. So see, I think some of you have this doubt. So you can actually apply approximations. See, when you are doing a big analysis, and you know that this approximate, if that approximation is not changing, not making any significant change, then you can actually approximate that. But generally, when a quiz question is asked specifically with some given data, then if you do certain approximations, then see, if it is a 1 mark quiz question, and there if you try to apply approximation, then you may deviate from your final answer, right? Because when you do a big analysis, you can actually bring in all the approximations to make your analysis easy. But a question is asked on a specific thing. Say for example, in your quiz also you had a question where you were asked to find V out by V in by giving V out by Vs and the resistance values. So even though there the V out by V in value is very small, slight difference from V out by Vs also, the question asked was specifically that. So in that case, you have to work out and give the answer for that. But whenever you do a big analysis and where you understand that it will not make any significant change, then you can actually put approximations. All right. Okay, now so this is input impedance. Now what about output impedance? What will be output impedance for this? Any idea? Output impedance? All right, that also we will do, and we will wind up for the day. Output impedance. So you can try and let me know what answer you are getting. So maybe I'll use the same equivalent circuit here. Yeah. So one thing to notice, whenever you find output impedance, you have to uh, nullify the effect of all the other sources. So input source I have grounded, right. Now this is the output terminal. So one more thing we know, since RE, whenever you find output impedance, you have to connect a test voltage. We are connecting a test voltage V test, and this is the current I test, and you should evaluate what is V test by I test, right. But when we do this evaluation V test by I test, since RE is coming in parallel to this V test, I can keep RE aside, and for the final R out I can say that this RE will come in parallel to the value what I am evaluating by V test by I test. Like this we can actually do this. So any answers? 1 by Gm parallel to R pi uh, parallel to Re. Okay. Any other answers? R pi parallel to Re parallel 1 by Gm. Re parallel to R pi. Okay. All right. Let us see. Let us see. Okay, it is Re. Yeah. Yes, Karthik, it is Re. Sorry. Okay, so to do this, what I will write here is, so I can actually take these two currents. What are these two currents? This current is the voltage across R pi is V pi. So that current is V pi by R pi plus Gm V pi and plus I test is equal to 0, right. So the sum of the currents, I am applying KCL at this node, incoming, incoming and incoming current. The sum of all those three is equal to 0. Now I can okay, give me a second. Yeah, so you can see that the voltage V test is actually, okay, let me write the relation between V pi and V test. So V pi is from ground to VE and V test is from E to ground. So V test is equal to minus V pi, right. That means I can write it as minus V test by R pi plus Gm into, sorry, not plus, it is minus Gm into V test plus I test is equal to 0, or I can write I test as V test into Gm plus 1 by R pi, right. So I can say V test by I test is equal to uh, R pi by 1 plus Gm R pi. Okay, so what is one GM R pi? GM R pi is beta, so this is equal to R pi by beta plus 1, which is equal to RE. So V test by I test, probably you would have realized this. Looking at emitter, we can directly write this. We have already done, right? The input impedance or the resistance looking at emitter is actually RE or 1 by GM. Now when you write the final, it is RE parallel to small re. I think some others you are getting some, yeah, RE is the answer. RE will come in parallel to capital RE. But I didn't get the other part. Some of you got it is 1 by GM parallel R pi parallel RE. You may need to check that once. All right. So this is the output impedance for a common collector. So with this, I'll wind up for the day and I can take questions now.